Welcome to Xiaol.x. Today we introduce SAPO, Soft Adaptive Policy Optimization, a flexible, data-driven framework engineered for real-time learning and smarter decision-making. Explore the future of adaptive intelligence right here.
Training AI isn't just hard, it's volatile. In reinforcement learning for large language models, tiny errors at each token are multiplied across a whole sequence. The result? Exploding or vanishing gradients and erratic updates. Enter SAPO, Stabilizing Advantage Policy Optimization.
Why do large language models sometimes spiral unpredictably when trained with reinforcement learning? Policy updates can push the model into steep reward cliffs. Gradients become noisy and the learning loop wobbles. High variance between exploration and exploitation creates volatility. One good reward, then a crash. Techniques like KL control.
Traditional GRPO and GSPO techniques rely on hard clipping. Anything outside an arbitrary band? Gone. The signal is flattened, and so is the information we could have learned from it. The result is huge waste. Researchers spend a third of their compute just fighting these dead zones.
Earlier, GRPO and GSPO optimizers used hard clipping. Any gradient that wandered beyond a tiny window was chopped to zero. The result? Information lost and data wasted. Our new approach doesn't slam the brakes. It scales back smoothly, keeping direction information and making use of every sample.
Imagine throwing away a perfect essay just because of a single typo. That's what standard training does every time it makes a wrong prediction. One negative update and the entire vocabulary shifts, jittering like this red wave. Instead, raise the temperature only for negative updates. The higher T-neg smooths the correction, keeping the rest.
Old sequence level methods judge an entire sample by a single bad token. One glitch, the whole thing gets tossed. Token level filtering flips that. It spots the bad token, removes it, and keeps everything else that still makes sense. The result? 95% of the data that used to be wasted is now training the model.
For years, outliers have been treated like brick walls, hard stops that break the flow of learning. SAPO offers a new path. On the left, it maintains global sequence coherence. On the right, it doesn't delete outliers, it softly gates them with a sec-squared curve, downweighting instead of discarding.
In signal processing, abrupt gates can create harsh, unnatural artifacts. SAPO introduces a different approach. Instead of chopping your signal off, it uses a soft gating mechanism based on the sec-squared function. That means no clipping, no hard edges, just clean, adaptive falloff.
Not all feedback is created equal. In language models, wrong predictions push on every logic, not just the mistaken one, causing a vocabulary-wide shift. This is why negative feedback is secretly much more dangerous than positive reinforcement. Gradient diffusion theory shows the fix.
Gradient diffusion explains why negative feedback can spiral out of control in large language models. When a model reuses its own output, errors propagate downhill, amplifying instability. The usual fix, lowering temperature, works for sampling, but applying it symmetrically chokes diversity and makes feedback loops brittle.
The difference between success and failure looks like the difference between these two shapes. On both AMY25 and HMMT25, SAPO climbs smoothly and then holds steady, about 80% normalized accuracy. The competing GRPO lines surge, then fall off a cliff. That early collapse means
Figure 1 tells the whole story. Traditional defenses drop off a cliff, a tiny input change, and the model collapses. SAPO replaces that cliff with a ramp. Graceful, controlled, and robust. The result? Predictions stay confident, even under pressure.
One line keeps soaring, while the others fall off a cliff. SAPO, our stable, adaptive policy optimization, reinforces its path, applies regularization to prevent forgetting, and holds high performance. GSPO and GRPO, they peak early, overfit, and collapse.
Old reinforcement learning optimizers often do great, right up until they fall off a cliff. Here, every prior method collapses around 40,000 iterations. Our SAPO optimizer stays calm, reaching 95% accuracy and holding steady.
We have bought more time, but the SAP is approved of the optimization. SAPO lets us guide Qwen3VL through stable, efficient, multimodal training. Structured steps, collect experience, update a
Stable Advantage Policy Optimization, SAPO, was designed to calm the wild swings of reinforcement learning. Compared with a standard policy gradient, SAPO's returns look steadier and far less volatile. It does this by redistributing probability mass toward promising actions, even when the action space is huge.
As models scale beyond the billion parameter era, stability becomes more than optimization. It's the foundation for progress. Reinforcement learning is still a maze of exploration, uncertainty, and reward design. SAPO helps keep training on track, but it's not the whole step. We need
it. Around the world, bold ideas are leaping out of the lab and into our lives. From AI-guided medicine and lifelike prosthetics to clean energy that powers rockets and cities. From immersive learning and precision farming to self-driving, self-charging vehicles and factories.
Welcome back to the deep dive. where we crack open the most cutting-edge research and distill it into knowledge you can use.
Today we're tackling a really interesting one, a new paper from the Quinn team at Alibaba.
It details a pretty big step forward in reinforcement learning, specifically for large language models. The whole thing is called Soft Adaptive Policy Optimization, or SAPO for short.
Right.
So our mission today is to take this really technical work and just explain how it deals with the volatility of AI training.
The chaos, really.
Exactly. And here's the hook for today. Have you ever wondered why training powerful AI models, especially these massive large language models, using reinforcement learning is so difficult?
It seems like it should be straightforward, doesn't it? You tell the model what's good, you tell it what's bad, and should adjust.
But it never is.
It's almost always dangerously volatile. And the whole problem, it really just boils down to one word. Stability?
Stability.
Yeah. So when an LLM generates some text, the RL algorithm has to decide how much to update the model. It uses this thing called a token level importance ratio to make that call.
And that's just comparing the new policy to the old one, right?
Exactly. It's the probability of a token under the new proposed policy versus its probability under the old one.
Okay, so if the new policy is way off from the old one, that ratio is going to be, what, really high or really low?
Precisely. And that's the problem. When the policy drifts even a tiny bit, and it does constantly, that ratio can have incredibly high variance. You get these gradient explosions.
So the update signals just become completely unpredictable.
Wildly inconsistent.
Yeah.
And it's even worse in these new complex models, like mixture of experts or MOE architectures.
Right, so you have these huge noisy gradients, they lead to messy updates, and sometimes the whole model's performance just collapses.
It falls off a cliff.
So the challenge this paper is trying to solve is finding a way to limit those really aggressive updates without accidentally killing the useful learning signals. We need control, not censorship.
A scalpel, not a hammer.
Okay, so let's unpack this. We should probably start with the blunt instrument researchers were using before this.
The old way.
The old way. So this was based on methods like GRPO and GSPO, and they relied on something called hard clipping.
Yeah, and hard is the right word. Hard clipping is like a fence post. Researchers had to manually define this really narrow band. It's usually denoted by the Greek letter epsilon day, around what they thought was the optimal update point.
And if the update went outside that?
If that importance ratio we talked about fell outside this tiny predefined band, the gradient was just hard clipped.
Meaning
the learning signal for that step was instantly set to 0, truncated, gone. It's a severe all or nothing decision.
That sounds incredibly difficult to tune in practice. You're basically asking researchers to set a single speed limit on a highway where the traffic and weather are changing every millisecond.
It's a nightmare. It requires just tons of manual hyperparameter tuning. And you have to find this perfect, precarious balance.
If your clipping band, your epsilon, is too tight,
you suppress perfectly good, useful samples just because the model was a little too enthusiastic. You hurt your learning, you hurt your sample efficiency.
If it's too loose,
then you let in all the noisy high variance gradients, and your training run just destabilizes. It's brittle. And finding that perfect epsilon value is mostly just trial and error that eats up huge amounts of compute time.
And to make it worse, these old methods couldn't even agree on where to do the clipping. You had GRPO, Group Relative Policy Optimization.
That one clipped at the token level. So a single word's contribution could get zeroed out if it was too extreme.
And then there was GSPO.
Group Sequence Policy Optimization. A bit more conservative, but it clipped at the sequence level. So if the whole sentence or paragraph was too far off policy, all the gradients for that entire sequence were just suppressed.
Wow. So you could be throwing away hundreds of good learning signals because of one or two bad tokens.
That's the definition of inefficient. And it perfectly defines the problem they're trying to solve. The industry needed something adaptive, something that could manage the noise without being so wasteful.
Which brings us to the new way. This is where SAPO comes in. Soft Adaptive Policy Optimization.
And the core idea is simple but brilliant. It replaces that rigid, all-or-nothing cliff face of hard clipping with a smooth, temperature-controlled soft gate.
I like the analogy in the paper. It's a ramp, not a brick wall.
It's spot on. Instead of a hard clip that just stops the learning signal dead, SAPO uses a continuous gating function. Mathematically, they use the set-squared function, which acts like a smooth curve.
A set-squared function. Okay, that's specific. What does that shape actually mean for the gradient in practice?
It means the system has a continuous trust region. So updates that are really close to being on policy are preserved at their full value. But as the importance ratio starts to deviate,
As it gets further off policy.
the gradient is just smoothly scaled down. It's
Oh.
attenuated, not chopped off.
So you still keep the direction and some of the information from the signal?
Exactly. Even for samples that are moderately off policy. And that directly translates to better sample efficiency and much, much better stability because you're not introducing these huge sudden shocks into the system.
I see. And the paper makes a big point about SAPO having this dual nature. It's sequence coherent like GSPO, but it's also token adaptive like GRPO.
And that combination is really powerful. So under normal conditions, SAPO acts coherently on the whole sequence, making sure the overall response makes sense. But the real magic is how it adapts under stress.
Give us an example.
Okay, imagine the model generates a paragraph with 100 tokens. Let's say 95 of those tokens are great, informative, neuron policy. But 5 of them are total outliers. The policy just went rogue for a second.
Okay.
GSPO, with its hard clipping, would see those 5 bad tokens, and it would suppress the gradients for the entire 100 token sequence.
You just wasted 95 perfectly good learning opportunities.
You did. But SAPO doesn't do that.
Yeah.
Because of that soft gate, it just selectively downweights the 5 offending outlier tokens that are causing the instability.
And it preserves the full signal from the other 95.
Exactly. It preserves the informative signal from everything that was near on policy. I mean, that is a fundamental difference in how you manage stability.
Okay, so we have this smooth adaptive ramp. It makes perfect sense. So why does the paper then immediately complicate things with asymmetric temperatures?
Yes.
They treat positive and negative updates differently. They set the temperature for negative tokens, this tau-deg, higher than for the positive ones, tau-pos. Why do that? Why the asymmetry?
This might be the most critical insight in the entire paper. And it all goes back to the massive size of an LLM's action space, its vocabulary. We have to think about the difference between a positive learning signal and a negative one. When you have a positive advantage, you're saying the token it picked was good and you want to increase its probability, that gradient is very focused.
Right. It just boosts that one successful action.
It primarily works to increase the logit, and therefore the probability, of that one single token. It's simple. It's stable.
Makes sense.
Now, consider a negative advantage, a penalty. You're trying to decrease the probability of the token it sampled because it was bad. But in an LLM, all the output probabilities for every token have to sum to 1. That's how the softmax function works.
So if you push the probability of one token down...
You are simultaneously forced to increase the probability of every other token in the vocabulary.
And the vocabulary in an LLM is enormous. Hundreds of thousands of tokens.
Precisely. So this negative gradient signal gets diffused across this massive action space. It ends up slightly increasing the logits of thousands upon thousands of unsampled irrelevant tokens. And that diffusion is what introduces this huge high variance noise. It dramatically increases the chance of a catastrophic update.
It's like trying to fix one little problem but accidentally messing with 1,000 other settings in the background. That sounds like a recipe for instability.
It is. This gradient diffusion is the main reason models tend towards what they call early collapse.
So the asymmetric temperature is the fix.
It's the fix. By setting a higher temperature for the negative tokens, the tau-neg, they force those high variance negative gradients to decay much more rapidly as the policy deviates.
So you're just dampening the most dangerous signal.
You're performing a targeted strike against the true source of the volatility. It significantly reduces the odds of a sudden training failure.
Okay, the theory is solid. Let's get to the evidence, the demo. The Quen team tested SAPO on math reasoning, multimodal benchmarks.
Yeah, specifically on their Quen 3VL models. They use both the mixture of experts and the dense versions.
So what were the most visually impressive results that really proved this whole thing works?
There are 3 visuals that just jump right out of the paper. The first one is figure 1. It's this visual comparison of the soft gate versus the cliff.
Okay.
If you plotted the gradient weighting function for the old methods, GRPO or GSPO, you'd see this sharp, abrupt step function. It's a cliff where the weighting just drops to 0 outside that fixed epsilon band.
And SQ.
SEPO's function, that sec-squared curve, is completely different. It peaks right at the optimal on policy point and then just gently rolls off. It decays smoothly, continuously. It's the perfect visual for controlled, stable policy adjustment.
It's a difference between a digital on-off switch and an analog dial.
That's a great way to put it. Then the second visual, figure 4, this is really the heart of the stability argument. You look at the training performance graph on these really tough benchmarks like A-mini-25.
Yeah.
SAPO's curve is just consistently smooth. An increasing reward. It's remarkably stable.
And what about the older methods on that same graph?
That's the kicker.
Yeah.
GSPO and GRPO are two. They show clear, undeniable evidence of early training collapse. You see the reward spike up for a bit, and then suddenly a sheer dramatic drop in performance. That's the noisy gradients destabilizing the model.
And SAPO just cruises right past that point.
Avoids the collapse entirely. It maintains a stable trajectory, and crucially, it achieves the highest final performance.
That's not just a technical win. For anyone running these jobs, that's a huge practical advantage. Stability means you're not wasting billions of GPU cycles restarting failed training runs.
It means predictable progress.
Yeah.
And then the third result, which is in figure 5, validates the most complex part, the asymmetric temperature. This is their ablation study, and it confirms exactly why having tau-beta greater than tau is so critical.
What did they find?
They tested different setups. They tried with the temperatures equal, then with the positive temperature slightly higher, and then with the negative one slightly higher. The training was by far the most stable and got the highest reward when the negative temperature was higher. On the flip side, when they put the higher temperature on the positive updates, the model had the most severe instability. It collapsed almost immediately.
That's just compelling proof. It shows that the diffusion of those negative gradients is the real Achilles heel, and this asymmetric softgate is the right tool to fix it.
It is. And the results hold up. SAPO delivered consistent gains when they were training these huge Qwen3 VL models on math, coding, logical reasoning. It really does transform the RL training environment.
It certainly sounds like it, but now we have to address the catch.
Right, there's always a catch.
While SAPO is clearly a massive improvement, it extends stable training by hundreds, maybe thousands of steps. The paper is honest that RL for LLMs is still fundamentally hard.
Very hard. They're still relying on an empirical assumption, which is that for most sequences, the policy isn't deviating catastrophically far off policy.
Just moderately.
It's moderately. And SAPO handles that token-level variance beautifully. It smooths out all those dangerous spikes. But it doesn't solve the core complexity of training these massive sparse networks.
I see.
I mean, we are asking a mixture of experts architecture to coordinate hundreds of billions of parameters across this giant dynamic action space. That underlying difficulty, the fundamental challenge of policy optimization itself, that's still there. SAPO is a brilliant and necessary mitigation tool. It's not a universal cure.
That's a good way to frame it. So SAPO gives us this powerful, adaptive, and reliable strategy. It turns the sharp corners of the older algorithms into these smooth, navigable curves, and that lets these huge models learn for much longer without blowing up.
Exactly. And the final thought for you to explore is this. As LLM vocabularies keep getting bigger, and as the industry keeps moving towards these massive, sparse MoE architectures, the pressure on optimization stability is only going to increase.
So the question is,
will smooth gating functions like SAPO become the absolute new default for all LLM fine-tuning? Or are there even deeper, stranger instabilities lurking in the future of, say, trillion-parameter models that we haven't even found names for yet?
something to mull over until our next deep dive. AI, the first frontier.